Okay, so this is Chapter 9. This is Section 9-4. This is recording number 2. We just did the previous example is the nursing home business. Now let's take a look at another example. I think these are a little hard, so I want to make sure I do enough of the examples for you. Okay, we're going to talk about the criminal arrest. A study found that in a random sample of 50 burglaries, 16% of the criminals were arrested. Okay, that was for burglaries. For the car thefts, same number, 50 car thefts, 12% were arrested. So we're going to have a margin of error, or our error budget. Yeah, I'm sorry, I said margin of error. I shouldn't have said that. It's not a margin of error. Our alpha, our error budget is 10%. Can it be concluded that the percentages of people who commit burglaries and were arrested is greater than the percentage of people who committed car thefts and were arrested? Okay, so as you can just imagine, this is a metaphor for many, 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 many types of problems. You're talking about 16% of a certain category, 12% of another category. Is there a difference between these two categories? What about public health type situations? Suppose that these percentages represented the percentages of adults versus the percentages of senior citizens versus the percentage, or you could have it percentages of young people. You could have it percentages of African Americans, percentages of Caucasians, percentages of men, percentages of women. Anything at all that you're dealing with percentages like this is the type of analysis that you would do. And this is what is so lacking in the public media and in the government, because they don't know how to do this. So somebody on KFI radio would say, well, listen, 16% here, 12% here. Obviously, this is a bigger number, so there's a difference. Well, it's not true. You have to do the mathematics to make a scientifically sound decision. Okay, so the hypothesis is very simple. It's P1 is equal to P2. That's the null hypothesis. The null hypothesis is always the same. You're always saying there is no difference. It's the status quo. Somebody has to prove. I'm demanding proof. Okay, and then here the claim is the researcher is claiming that P1, that's the percentages of burglaries, 16% is greater than 12%. That's the claim, that the population, that the P, not the P hat, the P is greater. P1 is greater than P2. Now, just think about it for a second. Why is it P1 greater than P2? Why do we say that? Why don't we say P hat? Well, the reason we don't say P hat is because that would be a trivial hypothesis, right? Because P hat is the sample proportion. Well, the sample proportion for P1 is 16, for P2 is 12, so obviously it's bigger. That's not the issue. The issue is whether or not the population proportion is different. Is this one bigger than this one? And we don't know, because we don't have the resources to examine the entire population. All we can do is look at the samples. And when we look at the samples, we draw an inference about the population. So that's what's always going on in a situation like this. Okay? All right. So, same song, second verse. Alpha is equal to for alpha of 0.10, it's a one-tailed test. So we come up with, by using the table, we come up with a z-value. The critical value is 1.28. We're going to draw our cartoon. There it is. There's our cartoon. It's a one-tailed test. Okay. Then we're going to compute the test value. Here's the formula for the test value. There's certain things that we need, so we calculate those as well. After we calculate those, we are going to come up with the test value. The test value is 0.58. So here's the test value, 0.58. Here's the critical value, 1.28. So we say, well, that number, the test value, is not big enough. It didn't go over into the critical region. Therefore, I do not have enough evidence to reject the null hypothesis. Okay? The null hypothesis is that they're equal. The claim, otherwise known as the research hypothesis, is that this guy is bigger than that guy. There's not enough evidence. There's not enough evidence to support the claim that the percentage of people who are arrested for burglary is greater than the percentage of people who are arrested who committed car thefts. So change this to make it more interesting to yourself. Let's say that instead of being arrested, maybe it's 16% versus 12% of something else. 16% of the people who, took the sugar pill got sick, and 12% of the people that took the medication didn't get sick. Whatever whatever you're interested in, it's the same exact analysis. Okay, so let's see where we are here. All right, so most of the section in the textbook deals with the so-called traditional method that we just did. That's finding the critical values, finding the test values, and so forth. But the author does talk briefly about p-value and the confidence interval methods. So just real quick here, we'll just look at that. The p-value for the difference of proportions, we find that from the table that we had that we did it before in section 9.1, 9-1. So remember, on the p-value, what we're looking for is what's the probability. P stands for probability, and it's unfortunate. The notation kind of makes you crazy because you can easily get this P mixed up with the P for proportion. But this P, the p-value, is the probability. So what's the probability of getting a z-value of 0.58 or more? So it's here or more. Well, how do you do it? You look at the table. So we're at 0.58. Now, in real life, this would all be done on your computer, but let's see if we can do this on our own. Okay, so it's really hard to do this on the screen because it's so hard to bounce back and forth. It's a lot easier for you to do it at home. So try to do this. So 0.58, that's my critical value. Or excuse me, I'm sorry, 0.58, that's my test value. That's what I get from my data, 0.58. Okay, I'm interested in what's the probability of getting something to the right of 0.58, to the right of 0.58. Well, my table only gives me information to the left, but I'm a smart guy. I know how to handle that. Let's take a look. So 0.58 is right here. 0.5, come across here, come across here, come across here. Gives me 0.7190. So it's 0.7190. Okay. So remember, on these z tables is always these numbers up here represent the area to the left of that z value. So for a z value that we're interested in of 0.58, it's 0.7190 or 71.9% of the area is to the left. But that's not what we want. We want the area to the right. So we take 1 subtract 0.7190. And what that gives us then is, as the book says, let's get back to that. Give me a second. Okay, I had some technical difficulties, so I hope I have good continuity here. So to the right of this number here is the 28%. That's a very large number. It's very, it's much higher, much bigger number than you'd ever get for any reasonable error. So using the p-value test, you would not reject the null hypothesis. Okay, so that's the p-value method of the hypothesis testing. The third way that we've been doing these is we've been doing the hypothesis testing using the confidence interval. So keep in mind that the variable that we're interested in is this P1 take away P2. That's the difference of the two proportions. Now remember, P, that's the population. So population 1 take away population 2. How do we estimate this delta? And then after we estimate it, how do we get the confidence interval? Well, as always, what we always do when we're trying to estimate the true population parameter of some sort, we always get a point estimate, and our point estimate is the p hat sub 1 and the p hat sub 2. So the p hat sub 1 and the p hat sub 2, you take that delta, that's your best estimate for what this is. Well, it's an estimate, so you got to have you have to have a plus or minus, right? So here's our estimate, p hat 1 take away p hat 2 plus or minus the margin of error. And here's the margin of error. And the margin of error is this guy, that's the standard error, multiplied by this number here. This is kind of a coefficient, I guess you would call it. And you find the appropriate z value that corresponds to this alpha over 2. Okay, so it's exactly like we did before when we were doing these confidence intervals. Kind of complicated, but it's a step-by-step process. I know you can do it, but you just don't be intimidated by it. Do it step by step and write out lots of notes to yourself to explain what you're doing. Don't just start writing things down. Okay, he explains here why sometimes you'll get a different answer. Okay, all right, take a look at this. So you're going to sometimes get a different answer, but that's not the end of the world. As long as you explain what you're doing, you know, if you're writing a paper or what have you. Okay, so let's do one quick example here, the 95% confidence interval. Okay, we got all of these things that we already did in example 9.9, and then we're going to plug it into this formula here. And what do we come up with? We come up with our best estimate. How much confidence do we have? We have a 95% confidence that the truth, the population difference, P1 take away P2, that's the population, that delta is somewhere between this number and this number. Okay, that's what we think the population delta is. Okay, so this was for example 9-9. All right, so that was the nursing home business. The null hypothesis in that case was that P1 and P2 were exactly equal, right? So the null hypothesis was that P1 take away P2 is 0. Well, is 0 between this number and this number? It is not. So what we're saying is that P1 take away P2 equaling 0 is not in this interval, it's outside of the interval. So since it's not inside the interval, we would reject that hypothesis. We would say, hey, it's not true. We're 95% sure that P1 take away P2, we're sure that it is not equal to 0. So we reject the null hypothesis. Now, this should be exactly what we concluded when we did it the other way. Let's take a look. Let me go up there. Okay, so this is 9-9. When we got to 9-9, we used the classical method, the traditional method, and we came up with a test value that was outside, that was in the rejection region. So we said, okay, there is enough evidence to reject the null hypothesis. There's enough evidence to reject the claim difference, which is right there. So we rejected the null hypothesis using that method as well. Okay, folks, that's about it. Here's another example. I urge you to spend as much time on this as you can. Here's an example here that might be of interest to you. Talking about, you got public schools and private schools. How many of the kids smoke? 32% versus 14%. Is that a significant difference or not? You know, that's the kind of the question that would be asked here in a situation like this. Okay, if there's enough information to answer it, I don't know. Yeah, down here it says, what information would you need to complete the statistical test? Okay. So if you look back up here for the test value, you need additional information, right? You need the n's, for example. Okay, you need the x1s and the n's. x1, n1, x2, n2, and I don't think you have that in this problem. That's the purpose of this problem, is to make you think about it and try to figure out, well, what do I really need and what don't I have? And if I was going to try to answer these questions, what would I have to ask for? Okay, it's kind of like in that first video I did when we talked about this new medication that they're saying gives you a better success rate. Just having a better success rate isn't good enough. That's like right here. Suppose this was suppose this was a medication and 32% of the people that took the placebo died and 14% of the people that took the medications lived. Is that statistically significant or not? It sounds like it would be, right? I mean, 32% died versus 14% died. You'd probably want to, take a bet on that, right? But you can't answer that question unless you have the additional information. You have to have the sample sizes and the actual number of successes. Okay, so I hope that helps you. Or you have to at least have to have the sample sizes, I guess I should say.